So our second speaker is Tim Hsieh from Perimeter Institute, and he's going to tell us about measurement protected quantum phases. Tim?
Okay, thanks, Susan. So yeah, let me begin by providing a little bit of context for this work. So this audience is certainly familiar with all sorts of different ultra-quantum phases of matter, which we know and love. And all of these are realizable as ground states of local Hamiltonians. And you know, in the past decade, there's been a lot of activity in exploring which of these orders and which new orders can be stabilized outside of ground states and even outside of thermal equilibrium. So a prime example is strongly disordered Hamiltonians of 1D systems, in which case one can have this phenomenon of many-body localization, which involves the breakdown of thermalization and restricted growth of entanglement. So as you probably know, this phenomenon of MBL enables you to have very highly excited states that are not only area law entangled, but have some kind of long-range order, both of which would be prohibited in some conventional thermalizing system. So in this case, it's strong disorder that plays the role for resulting in this breakdown and resulting in this restricted growth of entanglement. However, recently there's been a different approach at restricting entanglement growth and leading to area law states. And this is the setting of hybrid quantum circuits. So in these hybrid circuits, there are two components. They're both random unitary gates, as well as these projective measurements that are performed with some probability p. So the random unitaries want to entangle the whole system, and if they dominate, they'll lead to some volume law steady state. Whereas the projective measurements want to project degrees of freedom into product states and disentangle everything. So if they dominate, generically you'll get an area law phase. So this area law and volume law phase are separated by a very interesting phase transition that's been the subject of many recent works. So this competition between spreading and non-spreading may remind you of something, unfortunately, very close to heart these days. So hopefully, wherever you are, you're deep in this area law phase with respect to this perspective. But the thing is that this area law phase, it's obviously safer and preferable. But so far, the area law phase that have been considered are rather trivial and featureless, like many days in quarantine. So the question is, the question that we were interested in is, can you have some non-trivial long-range order that's stabilized in this hybrid circuit setting? So here's a brief overview of our work, which was done with my student Cheng-Shi Sang. So most details can be found in our preprint, although there will be some new important results that I'll present that we have not updated yet. And I also encourage you to check out related work from Mason Barkeshli's group at Maryland. Okay, so we were basically interested in the role of symmetry in these hybrid circuits. And we consider specifically a global Ising symmetry and two types of competing measurements. So we find that this global symmetry and a particular measurement enables one to have a spin glass area law phase. And moreover, it undergoes a direct transition to the paramagnetic volume law phase. And I'll present some evidence toward the end that this transition is actually in a new universality class compared to those studied previously due to this global symmetry. So here's the main setup we want to consider. So you have a brick wall circuit of 2-qubit operations. And with probability P, one does a projective measurement. And given that it's a measurement with probability R, you measure ZZ on the 2 qubits. And with probability 1 minus R, you measure X on the first qubit. Otherwise, you just apply a random unitary gate. So this unitary will not be completely random. So for the convenience of simulation, we'll want to consider a random Clifford unitary, which has the very nice property that it maps Pauli strings to Pauli strings. So this enables efficient classical simulation because one just has to keep track of how these Pauli strings are evolving under the dynamics. The more important restriction is the global symmetry. So we want to demand that this random unitary still commute with the global Ising symmetry given by the product of X operators. And notice that the measurements, the ZZ and X measurements, already obey this symmetry. So to satisfy the symmetry constraint, it's sufficient to demand that this random Clifford map the Pauli string XX to itself. Okay, so we'll be interested in the ensemble of steady states obtained by different realizations of this random hybrid circuit. And in particular, we're interested in the entanglement properties of the steady states. Are the area law or volume law entangled? And we'll also be interested in whether or not there's spin glass order in the steady state. So to quantify that, we use this order parameter shown here. So notice that for a trivial short-range entangled state, these correlation functions will decay exponentially with separation. And so then this order parameter will be constant or independent with system size L. On the other hand, in the spin glass phase, which you should think of as epitomized by a random cat state like this, of some random spin configuration plus the flipped partner. In this random Schrodinger cat-like state, the spin glass order parameter scales linearly with L. Notice that there's this power of 2 here, just to account for the randomness in the spin configuration. So these will be the 2 order parameters that we look at as a function of those probabilities P and R in the circuit. Okay, so let's consider some simple extreme limits. So let's consider first measurement only. So if you only have ZZ measurement only, then it's very simple. The steady state just has random zi plus 1 being plus or minus 1 for every pair. So this is the random cat state I referred to from the previous slide. You just end up with a steady state looking like this. And for such a state, the order parameter, the spin glass order parameter is exactly L. And in the other limit of X measurement only, you just get some random paramagnetic product state in which the order parameter is 1. And now let me give you a flavor for why the spin glass phase is stable to some amount of X measurement. So say you have a spin glass cluster in which all pairs of qubits have perfect ZZ correlation. Well, if you do an X measurement on 1 qubit, you'll project it out into some definite state. But the remaining qubits in that spin glass cluster will remain in that cluster. They'll still have perfect ZZ correlation. And at a later step, if you do a ZZ measurement involving the projected out qubit and 1 member of the cluster, then you can bring that qubit back into this cluster. And also, if you have multiple spin glass clusters, each with perfect ZZ correlation within themselves, and then you do a ZZ measurement involving one qubit from each cluster, then you'll just join them into a big spin glass cluster. Notice, however, that the symmetry is very important here. Because if one were to do a symmetry breaking measurement, for example, along the Z direction, then this would collapse the whole cat state and one would just end up with a product state. So it would immediately destroy this long range correlation. Okay, so now to go beyond these simple limits, it's convenient to use a Majorana representation for these operations. So this is a standard Jordan-Wigner transformation that represents each qubit by two corresponding Majorana modes. And now we can ask, what do these ZZ and X measurements correspond to? And so if you replace the two qubits by the corresponding four Majorana modes, then the ZZ measurement just maps to a fermion parity measurement for the two center Majoranas. And the other Majoranas just propagate forward unaffected. And similarly, the X measurement corresponds to the fermion parity on the first two Majoranas. So now this circuit with measurement only, if you just replace all these operators in the qubit language into the Majorana picture, you just end up with a bunch of loops, like a configuration shown here. And so in this picture, the spin glass phase and the paramagnetic phase correspond to regimes where you have short loops or with finite correlation length. And it's precisely when you have equal probability of these two measurements that you end up with a critical 2D classical loop model that's fully understood. And this is first pointed out in a very nice paper by Brian and Adam. Okay, so that's a story with measurements, and now we want to build in some unitaries. So what's nice is that the symmetric Clifford unitaries also have a good interpretation in terms of Majoranas. And this is because the global Ising symmetry maps to fermion parity symmetry in the Majorana language, which means that the unitary acting on two qubits maps to a unitary acting locally on the four Majoranas. So more specifically, it's not too hard to check that such symmetric Cliffords are generated by Majorana swap operations and an interaction which maps a single Majorana to the product of the other three, basically multiplication by the local fermion parity. So this is what the symmetric Cliffords look like in Majoranas. So now let's see what happens when you have some probability of unitary on top of this critical point with the measurement only model. So we have equal probability of ZZ and X, and now we tune P, the probability of measurement versus unitary. So shown here is the entanglement entropy as a function of log of the partition size, and for various probabilities P. So P equals 1 is the measurement only model I just described. That's described by the loop model. And indeed, if you just calculate the slope of this log L scaling, you find that it's consistent with the known classical loop model. But what was kind of surprising is that as you allow for some probability of unitary, so as you tune away from P equals 1, this entanglement scaling seems to remain critical all the way up to around P equals 0.5. And we also looked at mutual information and found that it scales as a power law in this regime between P equals 0.5 and 1. So of course we have to be aware of finite size effects, but for now let me just point out that we looked at pretty big systems up to almost 800 spins. Okay, so now let me consider another interesting cross-section in this phase diagram. which involves ZZ type measurements only, competing against unitaries. So, so shown here is, again, the entanglement entropy versus log of the partition size. And we identify a critical point at p equals 0.38 that separates the area law entangled phase with volume law entangled phase. And near this critical point, we can do what's now a pretty typical scaling collapse and find that they collapse quite nicely. And we can also look at the spin glass order parameter as a function of this probability p. And we find that at 0.39, the spin glass order parameter scales logarithmically with system size, indicating criticality. And this separates the paramagnetic phase from the spin glass phase. So 0.38, 0.39 are essentially the same within the resolution of our current numerics. So we claim that these two transitions occur at the same point. So we can also do a scaling collapse for the spin glass order parameter, and collapses pretty nicely. And we can extract critical exponents. Okay, so now let me provide some intuition for, first of all, why is the spin glass phase stable at all to symmetric unitaries? And secondly, why is there a simultaneous transition from spin glass to paramagnet and area law to volume law? So regarding the first question, at least on a very abstract level, spin glass phase has long range correlation. And so a finite depth unitary circuit cannot destroy that long range correlation. And the symmetry, again, is very important because one does not want to rotate to a symmetry breaking basis to do a measurement, because that would, as I showed you, collapse the long range correlation immediately. And regarding this question of the simultaneous transition, it's helpful to return to this Majorana representation. So here are the ZZ measurements and the unitaries in Majorana form again. And so now this hybrid circuit with ZZ and U's only looks something like this. And now one way to estimate the entanglement of an interval in the final state, let's say the entanglement of an interval bounded by these two spins A and B in the final state. One way to estimate that is to find the minimal cut through the circuit that that separates this interval from its complement. So by minimal cut, I mean some cut that passes through the fewest number of links through the history of the circuit. And so in this picture, the entanglement for this interval in the final state is given by the number of links that this minimal cut passes through. So in the area law phase, almost by definition, the minimal cut should pass through a constant number of links. Constant as in independent of the size of this interval, right? And the claim is that this minimal cut in the area law phase actually mediates long-range spin glass correlation between the two spins A and B at the boundary of this interval. So to see this explicitly, let's consider what's going on with the operations on this minimal cut. So at the base, you have this ZZ measurement performed, which results in maximal ZZ correlation for these two spins. And then slightly above, you have two more ZZ measurements performed. So these Z's cancel and one ends up with perfect ZZ correlation for these two. And this propagates up the minimal cut as shown all the way until you reach A and B, in which case you conclude that you have perfect ZZ correlation between A and B, even though you might have had some intervening unitaries contained in the interior of this cut. So this is a picture for why the area law phase is tied to the spin glass order, at least in this setup. So we expect that this minimal cut passing through constant number of links is no longer possible when the unitaries percolate. When that happens, any minimal cut will have to pass through an extensive number of links and give you volume law. So more concretely, we can just write this brick wall circuit as a rotated square lattice in which each dot now is either a ZZ measurement or unitary. And so just looking at Wikipedia, the side percolation threshold for square lattice is around 0.59, which is actually fairly close to this threshold probability of unitary we saw in the entanglement transition. Okay, so here's a summary of the full phase diagram in this model. So at the beginning, I told you about this paramagnetic spin glass transition for measurements only, whose critical point is described by that 2D classical loop model at r equals 0.5. I also told you about this cross-section, which involves spin glass area law to volume law paramagnetic transition. We also considered this cross-section here of adding some probability of unitary to this measurement-only critical point. And I showed you that even down to p equals 0.5, the entanglement scaling looked critical. So, aesthetically speaking, I am, and you probably are tempted to color this in blue, right? I mean, this just doesn't look very nice. But based on the numerics, we did not feel justified in doing that. So for now, let me just say that this is a critical regime that needs more finite size scaling to analyze.
Sorry, Tim,
what is unambiguous, however? Yeah.
Tim? Yeah. So
yes.
Is there still a self-duality somewhere in the phase diagram? Because actually, at least X and ZZ, at least algebraically, they are still dual to each other.
They are without the unitaries. So the random unitary, we did not enforce the XZZ duality for the random unitary, right? So the unitary will break that duality. So this is why we don't expect symmetry in the phase diagram.
Okay.
However, it could be that the random unitary only weakly breaks that duality, which might explain, why these phase boundaries look almost symmetric, right?
Hi, sorry, one more question here.
Yeah.
If you don't mind. So the scaling collapse was only done for the critical point on the edges of the phase diagram, but not inside the critical region. Is that correct?
Yeah, that's right. So we did it here and here.
I see. So was it difficult to do it in the middle, or it's just that it hasn't been done yet? Somehow the critical phase is somehow more difficult to access numerically.
Yeah, we just haven't done it yet.
Haven't done. Okay, all right.
But
I see.
Okay, so what is unambiguous is these two critical points, at least the one between paramagnetic and volume law, and the one between spin glass and volume law. And so these two critical points actually turn out to be already quite interesting. For this, we need a diagnostic that was used by these authors, and I thank Hsieh Chen for motivating us to look into this quantity. So they basically looked at the mutual information between two antipodal regions, A and B, as a function of the size of A. The size of B is the same. So what they found is that in the standard entanglement transition, so at the critical point between area law and volume law, this mutual information scales as a power of the size of A with power 4. Okay, and I'm told that this is a pretty good universal feature of this this critical point. So you can look at this in a variety of Clifford circuit architectures, and one is expected to get this slope for. However, if you look at this critical point between the paramagnetic and volume law phase first, we also did the exact same calculation for this circuit, and you actually find a different slope. So the claim is that this transition between area law and volume law phase in the presence of symmetry is in a different universality class than the one without symmetry. And for equilibrium phase transitions, it's not that surprising that symmetry is important. One needs it most of the time to define even a symmetry breaking phase. But this is a very unusual transition that involves involves volume versus area law entanglement. And so it's somewhat mysterious at this point exactly what the role of symmetry is in changing the universality class. And let me also point out that we also looked at this quantity for the spin glass volume law transition and found a different slope, 3/2. So this is clearly something that needs to be explained, and which we're working on. Okay. Yeah, I'm a little bit out of time, so let me just quickly mention that there are some interesting generalizations one can consider in higher dimensions. So in 3D, there's a possibility that these unitaries and measurement can both percolate in some parameter range. And so we did a simulation of a 2+1 hybrid with symmetric 4-qubit Clifford gates and pairwise easy measurements in this block here. And we find, so we looked at both the entanglement scaling, the gray and green plots, as well as the spin glass order parameters, the orange and red dots, as a function of the probability of measurement P. And we find that in this range 0.25 to 0.5, there is this coexistence of spin glass order and some super area law phase. At this point, we cannot conclusively say that it's volume law. It probably is, but with 2+1, one is more severely limited by finite size. And another interesting thing that can happen is, of course, topological order. So one can imagine, replacing these ZZ measurements by the star and plaquette measurements of Tor code, for example. And in this setup, one would speculate that a topologically ordered state can be stabilized in this hybrid circuit. So to diagnose that, one needs to generalize the spin glass order parameter to something a little bit more complicated, of some string connected correlator, as opposed to some on-site Z operator. So we haven't done that yet, but it may be interesting. And finally, let me just point out a comparison with active error correction. So as you may know, in architectures like the surface code, the goal is to preserve some logical state of a quantum system. And one does that by measuring stabilizers, the star and plaquette operators, for example. And based on the outcomes of those measurements, you know where the defects in your logical state are. So now you can try to basically annihilate those defects to restore that state that you're trying to preserve. So in contrast, in the hybrid circuit setting, we are doing these measurements, but we're not making use of the measurement results at all. And that's because we're not trying to preserve a particular state, but what ends up getting preserved is, you know, the pattern of long-range entanglement. So this is one distinction with active error correction. However, it would still be very interesting to explore what happens when you do make use of these measurement outcomes, and there's a whole phase space of conditioned unitaries based on the results. So yeah, so let me just summarize the main points. So we considered a hybrid measurement unitary circuit with a global Ising symmetry, found that there is a spin glass area law phase that undergoes transition to volume law phase. And these transitions look like they are in different universality classes than without symmetry. And yeah, there's also this mysterious critical regime based on our numerics that may or may not be finite size crossover. We still need to work on that. But even if not, it's interesting to ask, can there ever be some extended critical phase in an interacting hybrid circuit? So yeah, that's all I wanted to say, and thanks for your attention.
Thank you very much, Tim. Now we have some time for questions.
Hi, Tim. So I have a question about the unitary part of the circuit.
Yeah.
So if without that, we can certainly perform some sort of a you know, Kramer-Zwannian duality to sort of effectively map R to minus R in some sense, right? So just interchanging the paramagnet and the spin glass.
Right.
But somehow the introduction of the unitary kind of breaks that symmetry. Is that right? Is that the specific form of the unitary that you have chosen?
No, I mean this Kramer-Zwannian duality is basically a translation at the level of Majorana's.
Yes.
Right. And these the unitaries act on 2 qubits at a time.
Right.
So building in that translation symmetry at Majorana level is somewhat unnatural.
You mean that that unitary gate would actually become a non-local gate in, say, the dual representation?
No, the unitary is always local in terms of Majorana because of this symmetry constraint.
Right. Yes.
But you're asking for more, that it preserves, that the unitary ensemble preserves translation by single Majorana.
Yeah, well, I'm not saying that I need to include, I'm not saying that I want it to be symmetric in every single realization. I'm just saying that it seems like there's a different class of unitary that you could have included to interchange, I mean, such that the phase diagram that you get is sort of the mirror reflection of what you have right now.
Right.
And I'm just wondering if I have include everything. Maybe I need a 4th parameter, but I'm just saying that is this suggesting that I actually have a different kind of unitary and then maybe another axis out of this phase diagram to include, to maybe enrich everything, or
yeah, I mean it is interesting to try to enforce that symmetry for the unitary ensemble.
Okay.
Yeah, we just haven't done that.
Okay, so basically I guess I want to say that the current class of unitary, just by performing the Kramer-Zwannian duality, I would end up with a different class of random unitaries, not yet included in the existing model.
Sorry, I lost parts of that. My connection is not so good.
Sorry, okay, yeah, let me repeat that. So your random unitary belongs to a certain ensemble, but that ensemble doesn't seem to preserve the Kramer-Zwannian duality. That means either the ensemble can be deformed into preserving that, or there is a whole different class of random unitaries that is the image of the existing unitary ensemble under the Kramer-Zwannian duality. And I'm just wondering what these new, let's say, new ensemble or new class of unitary would do and would enrich this whole phase diagram.
Right.
Yeah. So that's just sort of a general comment.
Yeah. Thanks.
Yeah, can I ask something about the Tory code model? I mean, yeah, that in your to-do list. So actually, in the Tory code model, these two operators in the model, sorry, so all the operators in the model commute with each other, right?
Yes.
So do you expect, so when you run this, should be, I mean, still, so do you expect some big difference from the Ising case, or do you need to turn on some other terms that compete with these two terms?
Right. So what I had in mind was both star and plaquette terms together play the role of the ZZ thing in the previous.
So you have
there's no competition here, right? But yeah, well, one could add a competition, like a single site X, let's say. Right. And yeah, then right, there could be even richer phase diagram.
Tim, I have a question. Are there any ideas how to measure this topological order? Because again, one has to worry about this post-selection that you have.
Right. So yeah, in terms of physical realization, unfortunately, it's similar complexity as observing the vanilla entanglement transition.
I see.
Yeah.
So topological order doesn't add some doesn't make it easier. I would think probably not.
Not that we're aware of. It's again because the fact that the state is not a fixed state for every representation. It's only this pattern that's preserved, right? So to get any statistics, you do need.
And then, I see. And a related question: the state you are finally projecting to has some random values of some of these stabilizers, right? It's not like the.
That's right.
It's not like there's some preference for, say, ground state of Tory code, of course, because you're just measuring things. So, is there some way to do? If I think of it as a mixed state instead, and then is there some difference between then, say, 2D Tory code and 4D Tory code? Because in one case, maybe if you also have some kind of a thermal filter. Because if you think of the mixed state, and if you're projecting to some temperature less than critical temperature of 4D Tory code, then you have maybe you don't need to, then maybe makes life simpler, or you think there's no.
I'm not sure this addresses your question, but I think that the dimensionality would make a difference when you ask whether or not the topological order can exist in the volume law phase, right? So I only briefly mentioned this, but in the 2+1 setting, let's say our numerics, actually is finding this coexistence regime.
Right.
So then that's kind of like the existence of finite temperature order for 2D, as opposed to 1D. Right. So I think that would be the difference for 2D and 4D Tory code here. One could get this topological order within a volume law steady state. But for the mixed state picture, like for forgetting about the quantum trajectory, there I think one still runs into that same problem of just the measurements mixing everything up.
Okay. Yeah, I don't have any. Yeah, I was just thinking having some filter for the measurement so that you don't measure things which are more likely at above DC or something. So if you have that extra filter, then you don't ever get in that subspace of. Okay, it is very vague. I don't know. Yeah. Okay. Thanks.
Yeah, sure.
All right, if there are no further questions, thanks everyone for joining us, and let's thank both speakers again.
All right. Thanks.
All right. Have a good day. See you next week.
Yeah. See you.